All right, everyone, we are back and we're going to go through question number 4, complex stress states. So we look at the following scenario. We're going to be applying the stress state to our copper sheet. So the copper sheet, so we know our material is metallic, so Young's modulus is 100 GPa. Our Poisson ratio is equal to 0.3. We have, this is our stress in the 2-2 direction, which is negative. This is our stress in the 1-1 direction, which is positive. Top and bottom of our sheet, we don't have any bending. We have a linear thermal expansion coefficient here. We're dropping from room temperature, so that's our starting temperature. So that's our T initial. And then this is R, which is equal to room temperature 25 degrees C. And then this is going to be our T final. So our delta T is equal to T final minus T initial. You can keep it in centigrade here because it's just a delta. You can convert it to Kelvin, but again, it's not going to make a difference here. Resistance strain gauges are here. Gauge factor is this. When the stress state is applied to my Wheatstone bridge, it reads 6 millivolts. So we need to solve out for all the strains, write out the stress tensor for this problem, and then figure out our excitation voltage. Excellent. So what we're going to do is we're going to go over here and we're going to set up our solution. So we're given, this is lecture 6. I want to look at our exam notebook. All right, so our material, so y is equal to 100 times 10 to the 9th. We're also given nu is equal to 0.3. We're given our gauge factor is what? 3.2. Our V naught is equal to 6 times 10 to the minus 3. Our sig 22 is equal to negative 50 times 10 to the 6. Our sig 11 is equal to 10 times 10 to the 6. Our strain, our E11 is going to be equal to, actually we can, alpha equals 16 times 10 to the minus 6. Our delta T is equal to minus 123 minus 25. So final minus initial. Excellent. E11 is equal to 1 divided by y times sig 11 minus nu times sig 22. And then I'm going to call epsilon T is equal to alpha times delta T. Delta T. So this is plus ET. E22 equals 1 divided by y, sig 22 minus nu times sig 11 plus ET. And we know for this problem, my strain gauge in the one direction, even though it's in the bottom, is going to be measuring the strain equals E11. E2 equals E22. E4 equals E1. And then E3 also equals E1. And fantastic. So we're given all these values. So now let's see what we have left in our expression, because we want to set up the following system. So we want to say solve V naught divided by VI excitation equals F divided by 4 times E1 minus E2 minus E3 plus E4. And there you go. That's your excitation voltage. Fairly straightforward. Nice. If we want the measure of the strain, so E1, E2, E3, E4. And we can essentially see those values. Fantastic. Anything else in this problem? No. We got the excitation voltage. Stress tensor, I mean, we solved for the stresses already, and the stresses are actually given to us. So sigma 1, sig 2, and then everything else is 0, in case it's asking, but we're okay for there. Done. So we have a rosette. It has an angle of 80. So basically, it has a. I'm just going to draw it very arbitrarily. So I'm going to call this A, B, C. So an angle of 87 degrees between A and C. So this whole thing is 87. And and an angle of 38 between A and B. So this is the full rotation here. So this is 38 degrees here. So then we know the difference between B and C is going to be between 87 minus 38 degrees. We'll see if we want to leverage that later. So I'm actually measuring in my, so we have strain here, we have shear strain here, and what we're going to do in arm A, so in arm A we get 39. So we have a dashed line here at 39 microstrain. B is 121, so B is 121, and then C, 121, 320, so, and that is going to be equal to C. So we have to kind of decide where do we want to basically like start or like define our origin from. So for example, I can say, so we know that the circle is going to kind of encompass this. So maybe I start, so we want to do, where do we want to kind of move? I want to move ideally counterclockwise. So what I'm going to do is first, I want to define this triangle. So I need my center, I need this 2 theta, and I need this radius. And we're going to start from here, and then we're going to rotate. So basically starting from our C value, and we're going to go from to here and to here. Make sense? All right, let's get to it. So let's go ahead, and we're going to go up here. So I'm going to say that my EA equals 39 times 10 to the minus 6. EB equals 121 times 10 to the minus 6. And then EC equals 320 times 10 to the minus 6. So those are my 3 strains. So I'm going to say equation 1 equals, or actually, I'm going to say EQ1 equals EA. Actually, let's start with EC. So we're saying that EC, like we're going to start this definition, is equal to the center plus the radius and then this 2 theta value, right? Because if I add on here, I'll hit that value for that triangle. So we're going to rotate relative to that. So EC is going to be equal to center plus my radius times cosine of 2 theta. And then we're going to have degree. Excellent. So that's equation 1. Equation 2, so now we're rotating, and we're rotating counterclockwise. EB equals C plus R times cosine. Now that angle is basically 87 minus 38, and we're going to do twice that. So 2 times the angle theta plus 49 times 2 degree, and then it doesn't hurt if you put a degree here as well, but it should read the full thing as degree mode. Excellent. And then finally, our last equation here, equation 3, we'll move to A. We know it's 87, but same thing. So 3 equations, 3 unknowns. We know the relationship between these. So now I can go ahead and say solve EQ1, EQ2, EQ3. Let's just do, say, numerically. So we can see here our center will be at this value, our radius is this, and then the angle here, at least in that first value, is just going to be, oops, let's copy and paste this here, is going to be 8.3 degrees. So that's that angle, that 2 theta angle, or actually it's a theta angle, 2 theta will be twice that. But that is essentially the rotation there to get there. Fantastic. Yeah, the A and C is 87. So that's pretty much all. That's the rotation to get to that principal stress. So you would rotate, if this is the angle, you'd rotate that basically in this direction to get there. Fantastic. That is everything. So thank you so much, and we'll see you on the next exam when we get into controls. Thanks. Bye.